Today, our group is going to discuss about graphical sensitivity analysis. But before that, we're going to define what is sensitivity analysis. A sensitivity analysis is determine how different values of an independent variable affect a particular dependent variable in a given set of assumptions. In other words, sensitivity analysis studies how various sources of uncertainty in a mathematical model contribute to the models of overall uncertainty. This technique is used within specific boundaries that depend on one or more variables. Sensitivity analysis is used in the business world and in the field of economics. It is commonly used by financial analysts and economists, and it is also known as what-if analysis. Now, how sensitivity analysis works? Sensitivity analysis works as a financial model that determines how target variables are affected based on changes on other variables known as input variables. This model is referred to as what-if or simulation analysis. It is a way to predict the outcome of a decision given a certain range of variables. By creating a given set of variables, an analyst can determine how changes one variable affect the outcome. To the following, we're going to show some of the examples, some problems that has been analyzed and solved using the graphical sensitivity analysis. So,
in the graphical analysis, this is the shelving example. If we measure the number of S shelves along the horizontal axis and the number of LX along the vertical axis or vice versa, every solution can be uniquely represented as a point in the plane. This is the figure 1. Graphical analysis. To represent the model graphically, we start by identifying the so-called feasible region, the part of the plane which contains all feasible solutions. The feasible region is determined by considering each of the constraints sequentially. It does not matter in what specific sequence the constraints are enumerated. Recall that in a linear program, each constraint is either a linear equation or a linear inequality. Before we continue, first a quick review of the graphical representation of such equations or inequalities. So linear equations. A linear equation corresponds, as the term linear indicates, with a line. A line is uniquely determined by 2 points on the line. In those suffices points on the line. Often, it is convenient to find the points in intersection with the vertical and horizontal side. So, this is the example. The equation is 0.25s plus 0.5lx equals 800. So, the point on the x-axis is obtained by the setting lx equals 0, though 0.25s equals 800 or s equals 3200. The point of the lx axis is obtained by setting s equals 0, those 0.5 lx equals 800 or lx equals 1600. So we conclude that the equation is 0.25s plus 0.5 lx equals 800 corresponds with the line going to the point s or lx equals 3200 and 0, and s and lx equals 0 on 1600.
We are now to determine the feasible region. What is feasible region? Feasible region is a set of all points whose coordinates satisfy the constraints of a problem. For example of constraints, we sequentially introduce each of the constraints, identify the line or half-plane corresponding with the constraint, and keep track of the intersection with the feasible region identified thus far. Figure 3 shows the half plane corresponding with the S assembly constraint S less than or equal to 1900. The set of points which satisfy these constraints and the negativity constraints S greater than or equal to 0, Lx greater than or equal to 0 is thus given by the rectangle bordered by the S-axis and the lines S equals 0 and S equals 1900. Here are the figure 3. Here are also the figure 4 introduces the Lx assembly constraint. The set of points which satisfy this constraint is given by the half plane below the horizontal line Lx equals 1400. The set of points which are feasible with respect to both assembly constraints and the non-negativity constraint is thus given by the shaded rectangle.
Now, next example is figure 5, which introduces the stamping constraint. The half plane below the stamping line represents all points that are feasible with respect to this constraint taken by itself. As you can see on the screen, the shaded pentagon is the region of points which are feasible with respect to the first 3 constraints and non-negativity constraints. Finally, figure 6 adds the last example, which is the forming constraint, and show how the feasible region again reduces. Now, you can see on the screen the smaller shaded pentagon.
Welcome! In this tutorial, I will solve this LP problem using graphical approach and use it to explain the special case of alternative or multiple optimal solutions. Let's begin by finding points for drawing the constraint lines. For the first constraint line, when x is 0, y is 60, and when y is 0, x is 120. For the second, when x is 0, y is 60, and when y is 0, x is also 60. For the third, when x is 0, y is also 0. So to find another point, we can rewrite the inequality as x greater or equal to 2y. We can then pick a reasonable value for either x or y and calculate the other. For instance, if y is 50, x is 2 times 50, which gives 100. Let's now draw the graph. Here are the constraints along with the xy coordinate pairs obtained earlier. Since the highest x value we have here is 120 and the highest y is 60, we can go up to 120 on the x-axis and up to 60 on the y-axis. For the first constraint, we have 0, 60 and 120, 0. We join the points for the constraint line. For the second, we have 0, 60 and 60, 0, and that's the line. For the third constraint, we have a point at 0, 0 and another at 150, and that's the line in gray. Now, the first constraint is a less than constraint, satisfied below the line in the direction of the origin here. The second is a greater than constraint, satisfied above the line away from the origin. The third constraint, however, is not as innocent as it looks because it has a negative sign. You should exercise extra caution when determining the direction satisfying a constraint with negative coefficients. I will suggest choosing a test point on either side of a line and then testing to see if that point satisfies the given constraint. Let's take this point 0, 30 for example. Putting it in the left side of the constraint gives negative 60, which is not greater than 0. In other words, the constraint is not satisfied in that direction. Just to confirm that it is satisfied in the opposite direction, let's try this point 40, 0. Substituting 40, 0 gives 40 on the left side, which is clearly greater than 0. So the third constraint is satisfied in this direction here. By observing the directions of the arrows, we see that the region satisfying all 3 constraints simultaneously is this one here, which we call the feasible region. Now, the LP concept states that the optimal solution will occur at one of these corner or extreme points of the feasible region. It is easy to investigate all four extreme points here as they all fall on grids, but I'm just going to use the objective function or isoprofit line. Profit, since this is a maximization problem. The objective function is to maximize z equals 5x plus 10y. I can create an instance of a line by simply multiplying 5 and 10 here, which gives 50, and drawing the line 5x plus 10y equals 50. But that won't really display well on this graph. So I can use multiples of 50, like 100 or 200. Let's just use 100. So for the profit line, when x is 0, y is 10, and when y is 0, x is 20. Thus, we have an instance of the profit line here. We now move the profit line increasingly until it touches the most extreme or corner point of the feasible region. But here we have it touching two corners simultaneously and lying entirely on a constraint line. The coordinates at the top here are easily identified to be x equals 60 and y equals 30. And plugging it into the objective function gives z equals 600. The coordinates at the corner down here are x equals 120 and y equals 0. And that also gives a z of 600. In other words, we have alternative or multiple optimal solutions. This essentially happens when a constraint touching an optimal solution point, that is, a binding constraint, is parallel to the objective function line. Note that the left side of the first constraint is 1x plus 2y. And when you multiply that by 5, you obtain the objective function. Note also that not only these two corners are optimal solutions. Every point on the line between them is also optimal and will give a z value of 600. For example, the value of z at this point 8020 is 600, and the z value at 110 here is also 600. And that's it for this video. Thanks for watching.
About our topic, which is graphical sensitivity analysis for variable linear programming problems. So a sensitivity analysis is analogous in taking extra precautions against paint spatters. Extra precautions are taken against uncertainty when estimating certain objective functions such as profit. In graphical sensitivity analysis, two-dimensional graphs are used in order to depict changes when problem coefficients or constants have been attained because of better estimation. So there are three fundamental elements of graphical sensitivity analysis. First is linear problem variables or decision variables, in which quantities have been determined. Second is objective function, in which a function that needs to be either minimized or maximized in order to find an optimal solution. It is more often a profit function, and the problem's optimal solution has to do with the profit maximization. Third is constraints, are linear inequalities, which includes decision variables. So there are advantages in conducting sensitivity analysis because it provides a number of benefits for decision makers. First is that it acts as an in-depth study for all the variables because it's more in-depth. The predictions may be far more reliable. Second is that it allows decision makers to identify where they can make more improvements in the future. Finally, it allows for the ability to make sound decisions about the company, the economy, and their instruments. Then, there are also some disadvantages in using this such kind of model. The outcomes are all based in assumptions because the variables are all based on historical data. This means that it isn't exactly accurate, so there are more room for error when applying the analysis to future predictions.